Now, the next question here. The structure of polymer A and polymer B are given in this way. This is about polymerization. In the boxes below, identify the monomers from which these polymers are made. You can clearly see that this polymer A involves an ester link. There's a CH2CH2. It must have had two alcohol bits at the two ends. And here's a C double bond O, CH2, C double bond O. It's like a propanoic acid, but it's a propandioic acid with the acid bits at each end of that 3-carbon molecule. And that's an ester linkage on the left, and this is an ester linkage on the right. That sort of polymerization, when you get a small molecule like a water or an ammonia ejected or a hydrogen chloride, that's called a condensation polymerization. On the other hand, with polymer B, how that's formed is this. There would have been a double bond between these two carbons, where I'm pointing to now, a double bond there. And over here you would have had another of the same molecule with a double bond here. And here, those double bonds open up and the two molecules combine. And likewise, because the double bond opened up, there's a bond on the left and over here a bond on the right. That process keeps going on ad infinitum to give you a very long chain addition polymer. Okay. Now, how can we identify these? So I said over here you have CH2CH2 with OH groups on either end. So there you have one of the monomers that's needed for polymer A. The other monomer will be the alkanoic acid with the CH2 in the middle and the two C double bond OHs at the two ends. That's actually called propandioic acid because there are two alkanoic acid functional groups. So those combine together to give that condensation polymer. Now look at this one here. Here's the double bond here where it was CH2CH. There we are, double bond between them, and C2H5 there, an ethyl group. If you have lots of those next to each other, this double bond can open apart and then they can combine together to give this addition polymer. And that would be, in this case then, but1ene. Part B says, one of the polymers from above can be hydrolyzed using sodium hydroxide solution. Identify the polymer and draw the structures for the organic products of the hydrolysis. Now look at the polymer here. This one here, there's no such reaction with OH minus. That doesn't break carbon-carbon single bonds, right? Warming with a sodium hydroxide solution doesn't break carbon-carbon single bonds. So it can't be polymer B. But polymer A, you can break it up by warming with sodium hydroxide solution. Why? Because the links here between the two separate monomers are ester linkages. So warming with hydroxide ions can break the ester link, and what do you first get? Alkanoic acid and alcohol. And the alcohol stays as an alcohol. But under alkaline conditions, what does the alkanoic acid do? You end up with the corresponding alkanoate ion. So, one of the polymers above can be hydrolyzed using sodium hydroxide solution. Identify the polymer, that's polymer A, that's why we've written it there like that, and draw the structures for the organic products of the hydrolysis. So, they wanted to see whether you could identify the two molecules, and of course under alkaline conditions, if you gave the acid, you wouldn't have got the full mark because the acid then reacts with the alkali to give you the alkanoate ion. And of course, there are two acid bits at the two ends. So that's why you end up with the C double bond O minus at each end of the acid molecule. And the other product, of course, is our 2-carbon alcohol with the OHs at the two ends. So that's the organic products that are formed as a result of that alkaline hydrolysis to break up this polymer A. Now, question 7 continues. It says in part C, nylon 610 can be made from the monomers below. That's this one here, 1,6-diaminohexane, this one here, and this other stuff called sebacoyl chloride, which is this one here. Can you see, first of all, that the Amine has got NH2s at both ends. Acid chloride has got acid chloride functional groups at both ends. So therefore, in this situation, it's possible to get a continuous chain polymer being formed, because what will happen? You will have, I told you, the acid chlorides react with amines to produce an amide link. So it tells you here the steps for the formation of nylon 610. They are given below. You might have even done this as an experiment at school. 2 grams of the diamine is dissolved in 25 mils of water. 2.5 mils of sebacoyl chloride, that's this one here, is dissolved in 25 mil of a non-polar organic solvent. Now think about it. Why would you dissolve that in a non-polar organic solvent? What will happen to this if you put water into it? That's not going to stay like that. You will end up with OH groups where the chlorines are. So unless you wanted that to happen, you wouldn't put it in water. You use a non-polar organic solvent, because this is highly reactive. An alkyl chloride, and it will react with water to replace the chlorines with OH. But we don't want that happening. We want this reacting with those hydrogens from there. The dissolved sebacoyl chloride is poured into the diamine solution. So you put that into there. 5 grams of sodium hydrogen carbonate is added. The nylon is extracted from the interface between the diamine and the sebacoyl chloride layers. Now, identify the repeating unit of the polymer form. Understand it carefully. I've drawn them in the 2 different colors so you can identify them. The amine part, right, or the diamine part, I've drawn in the green. So you can see you'll have a NH, which will have a bond. That's not a minus sign. I'm pointing to a bond this time. Okay. That will continue to link to the next red unit on its left. But that NH, so one of the H's has gone away. And then there's a CH2 6 times here. Then you have another NH, and its H has gone away with that chlorine to eject a small HCl molecule, hydrogen chloride molecule. So this is again a polymerization. Typically in condensation polymerizations, the small molecule that's ejected is either an H2O or an ammonia, or like in this instance, a hydrogen chloride molecule. So then the green H from there will combine with that chlorine to produce a hydrogen chloride molecule, and then the rest combine. See, C double bond O, CH2 8 times, C double bond O. Then at this end, this chlorine comes off by reacting with a hydrogen from there, and then they'll link together as an NH in green, and that process continues to the right. So that's what happens here. Identify the repeating unit of the polymer form. That's this thing here that you had to draw, okay? You could have even had the red part on the left and the green part on the right. It's just as valid. Okay. Explain why the diamine is water soluble. So what we have to do is to explain why a diamine like this is water soluble. Why are amines in fact water soluble? Because they undergo hydrogen bonding with water molecules. Why is that possible? Because you have a nitrogen connected to a hydrogen atom. So you can say, there is a complete explanation of that. The diamine has hydrogens linked to nitrogen atoms. This makes it possible for them to hydrogen bond, or this makes it possible for them to undergo hydrogen bonding with H2O molecules. Hence, water soluble. Okay. Other things where this sort of hydrogen bonding happens and things become very water soluble, you know one that's a very good example. Ammonia, NH3, it is highly soluble in water. Why? That also has hydrogens connected to nitrogen atoms. And then they can undergo hydrogen bonding interactions with water molecules. Okay. In sugars, sugar is very soluble in water. Why? Sugar has lots of OHs, not nitrogens, but lots of OHs. So you have hydrogens connected to oxygens. There as well, you have hydrogen bonding interactions. Okay. Now, So we explained the second bullet point. The third bullet point, explain why the subaqueous chloride is dissolved in a non-polar organic solvent. I already answered that along the way, because it will react violently with water, where the Cls will get replaced as OH groups to produce alkanoic acid groups. Right? But we want that Cl there so it can react with this NH2 group to form the amide link. Explain why the sodium hydrogen carbonate is added. The sodium hydrogen carbonate, HCO3 minus, is a base. It reacts with the acid to give you H2O, CO2, and of course Na plus and Cl minus. If you didn't remove the HCl, what will it do? The acid can hydrolyze the amide link and it will destroy the nylon as soon as it is formed.